the Healthcare Intelligence Group at Microsoft Research in Cambridge. This is a fairly new group, and we focus on 4 main areas. One is mental health, hospital care, immunomics, and imaging. We pick these areas because they meet current unmet needs, as well as because they're important research areas for the way we practice medicine in the future. In hospital care, we're looking at how to optimize clinical workflows using a combination of machine learning as well as an ethnographic understanding of clinical practices. In mental health, we're combining machine learning with human-centered AI to help patients who suffer from mild to moderate depression. We're also working on deep generative models in the immunomic space to kind of figure out robust diagnostics, trying to figure out the TCR to antigen map. And today I'm going to talk about the imaging work that we do. So this project is called Project InnerEye, and it's about building productivity tools for clinicians. And needless to say, we're using AI or machine learning to accomplish this. So more specifically, InnerEye develops state-of-the-art machine learning for medical image analysis to enhance clinical decision-making, clinical workflows, and patient outcomes. So in this talk, I'll focus on cancer treatment workflows. So when we talk about cancer treatment, there are 3 main ways of treating patients, as most of you know. The first is surgery, where a surgeon physically removes the tumor from the body. The second is chemotherapy, where we use drugs to kill cancer cells. The third is radiotherapy, where we use high doses of radiation to kill cancer cells and shrink tumors. In radiotherapy, we use a linear accelerator, LINAC, for radiotherapy delivery, as shown over here. The LINAC requires an execution plan in order to maximize the radiation dose over the cancer cells and minimize it on the healthy tissues. So how do we create this plan? So first, we scan the patient in 3 dimensions with a CT scan, and then the clinician must trace the anatomy with high precision, as shown here to the right. So the clinician here is delineating the target tumor and the organs at risk. And what we can see over here is a tool that is typically used by clinicians today, where they need to go through dozens of slices delineating multiple structures. And this can take anywhere between 20 minutes to a few hours, depending on the type of tumor being targeted. So when we look at the full workflow for radiotherapy, we can see that first the clinician needs to acquire the planning scans, and then the clinician needs to draw on these images to create a dose plan. After that, the patient comes back for multiple fractions of radiotherapy treatment, and the same plan is used for all of them. Obviously, this is not optimal, as things change during the treatment. The size of the tumor might change, the anatomy might change, and with automatic segmentation, the plan we hope to efficiently plan for every fraction that is delivered, thus enabling new workflows such as adaptive radiotherapy, where multiple plans are done during the treatment. So let me quickly give you a demonstration of our auto-segmentation tool. What you see over here is a tool that allows us to label images to train auto-segmentation models. It also allows us to invoke the segmentation service that is running on a cloud. So here, as you can see, we've opened a 3-dimensional CT scan for a patient suffering from prostate cancer, and we've also selected the prostate cancer model, which will be applied in the cloud. So this scan is anonymized and compressed and then sent to the cloud, and then the cloud service will receive the image and start applying our auto-segmentation model to every single voxel in the image. And by doing so, it looks around every voxel to figure out the context surrounding the area of the voxel, and then deciding what class or which of the first of one of the 6 structures that we are interested in that voxel belongs to. So what we're doing here is asking the model to segment 6 structures: the femurs, the bladder, the rectum, the prostate, and the seminal vesicles. And in a bit, you'll see that the results are sent back to the client, and the clinician has the opportunity to review the results. So over here, we have the segmentation results corresponding to the 6 structures of interest. And the clinician here is observing the results in the axial view. We also have the coronal and sagittal views, and eventually she's going to look at the three-dimensional view as well. What we provided this tool is also correction tools so that the clinician can refine the results so that they meet the clinician's expectations. So the point is that the tool is there to augment the clinician so that they can do their work much more effectively. So here the clinician is inspecting the bladder, and then the tumor, of course, the prostate, and so on and so forth. And as you can see, the entire end-to-end process of actually coming up with the segmentation has been reduced from hours to a matter of minutes. So the hope is that machine learning produces the automatic contours, and which is followed by a close inspection of the quality of the contours by the clinician, who fixes them up so that they can actually be used for dose calculation. So with that introduction, let me talk about the machine learning that drives this kind of technology. So as we all know, machine learning is everywhere and manifests in various forms. Here are a few examples of popular machine learning applications. To the bottom over there, we have the Skype translator, which is a live translation service. Then we have smart speakers from Amazon, and we also have recommendation systems which suggest shopping recommendations. And here's an example of a classification task. Over here, we'd like to recognize sharks and lizards. And machine learning here involves learning a representation of features such that it is possible to cleanly categorize the sharks and the lizards. So for example, here's a 2D representation that could potentially be learned by a machine learning algorithm. And as you can see, there's a clean separation between the sharks to the left and the lizards to the right. So it's about learning a latent space where you can very cleanly separate these features. And likewise, here's another visualization of the sharks and lizards in 3D space. And again, machine learning has learned a clean separation, and that's the whole objective of doing effective learning. So having learned this representation, the classification scheme would learn a function that, again, cleanly separates the sharks from the lizards. And at inference time, or at test time, when you get a picture of a lizard or a shark, if it goes to the left, you'd like to believe that that's a shark, and if it goes to the right, you'd like to believe that it's a lizard. So here's another example of a visual recognition system in Microsoft Kinect, where the input is a depth image, and the output is a body part segmentation, where every pixel is classified into various parts of the body. And every color over there represents a body part, and this was developed in our lab in Cambridge and formed a crucial component of the Kinect system. So let me quickly go through a very simple algorithm that is used to actually perform this task. So the underlying technology for Kinect happens to be based on a decision tree. As most of you know, a decision tree is just a binary tree with a root node, internal nodes, and terminal leaves. And from a machine learning standpoint, if we'd like to kind of take that picture and ask the question whether it's an indoor scene or an outdoor scene, what the decision tree algorithm learns are various questions that would be asked at every node. And if a question is true, you go to the right, and if it's false, you go to the left. Right? For example, in this picture, the root node asks the question: is the top part of the picture blue? If yes, in this case it's yes, it goes and asks the next question: is the bottom part blue? And that's false, and therefore it goes to the leaf node and basically deems this picture to be an outdoor scene. Right. So given an input, the path traced by the decision tree leads to a leaf node, which is this histogram shown over here, and this can be looked upon as a probabilistic prediction of the probability of each class having a particular value, so that can be used to decide whether it's an indoor scene or an outdoor scene. In Kinect, we use a generalization of trees, and these are called forests, which is an ensemble of trees. And it's known, and we've shown that looking at forests as opposed to trees leads to better generalization. And the idea is very simple. So we look at the kind of the predictions from each of the trees, And there are a number of ways by means of which you can combine these predictions. So the first, or the second graph basically says that we combine the decisions of each of the individual trees by taking a mean. This one says the product. You could take a median and so on and so forth, depending on the application. So that broadly describes the simple algorithm that drives Microsoft Connect. So in InnerEye, we're working on similar problems where the input images now are radiological scans, and the output is the segmentation or pixel or voxel-wise classification for various parts of the body. So in other words, we're building on several years of research and machine learning expertise to automagically perhaps perform semantic segmentation of radiological scans. So what is the goal of 3D segmentation? Here we have two axial scans of a patient, a CT scan of the pelvis part of the body, and the goal here is to segment this scan into the prostate, the seminal vesicles, the rectum, bladder, left and right femurs, and the skin. And of course, we want to do this automatically using machine learning. So what this involves is a pixel-wise, or in this case, a voxel-wise classification of each of these voxels into the structures that I mentioned before. And this is a particularly hard problem due to a number of factors listed to the right. And to name a few, the intensities can be the same for different anatomies. So over here, we have the intensity for the rectum being the same as that for the bladder. And there could be other image characteristics that can be wildly different due to various artifacts, the presence of contrast agent, and so on and so forth. So given all these challenges, the question is, how does one robustly come up with a segmentation? And furthermore, when we started this project, it was really hard for us to get access to large data sets of labeled images, which is really required for machine learning. And in our case, we had access to a few hundreds of images. So our research agenda was centered around how does one get to clinical grade segmentations from a very small number of images. So how do you learn from a small number of images? So key property of the algorithm is that it needs to effectively capture context. And as you can see over here, given a reference voxel, we have these probe voxels which kind of define the context, and this is for the voxel to get a sense for what its neighborhood looks like. And over here, the probe voxels correspond to the femurs, the seminal vesicle, and the rectum. Right? And these probe voxels form a part of the feature vector. So I remember when we started off describing machine learning, key part is actually learning the right kinds of feature vectors, and in our algorithm, these form the components of the vectors of the algorithm for each reference voxel. So given every voxel, we translate that into this kind of a feature vector. And for given an image, we can actually, and given this vector representation, the whole problem is to basically learn these classifiers which separate these voxels into the various structures. And the algorithm or model that we use is a deep decision forest, which is our addition to standard decision forests. So let me quickly show you how this works. So here we have an input CT image, and each voxel in this image, as you saw earlier, traverses a path in the forest, giving us a probability map. So for example, that probability map describes the probability of the voxel being either a bladder or prostate, and so on and so forth. And from a technical standpoint, what we need to do is to make sure that these forests generalize well from a small number of examples, training examples. And for that, there are two innovations to the standard deep decision forest algorithm that we employ. The first is that we have a forest that actually does some kind of latent clustering to deal with severe class imbalance that usually arises from medical images. As most of you know, most of the image is dominated by the background, and that really can be quite confusing because it presents the image in particular presents very weak signals for the machine learning to learn from. So there's a lot of noise. So we have a latent clustering algorithm which in a fairly semi-supervised manner deals with class imbalance. And the second innovation is node level cross-validation, and this basically boils down to having a special cost function that can actually generalize well from a very small number of examples. So as I mentioned, each voxel induces a probability map, which basically means that given an image, what the forest translates that into is a output which looks like a probability map for the whole image. Now this image this probability map is used in conjunction with the image to learn a new set of parameters. So in the next step, what we do is we take the probability map from the earlier iteration and feed that back to the algorithms to learn another forest layer. So, and thereby we basically learn a cascade of forest layers. So again, we repeat this process again for another forest layer, and this process continues until we learn a final segmentation layer for the problem. So this is another form of deep learning. So the question to ask is, where are the convolutions, right? Because that's what we see over and over again when one does regular deep learning. So what the forest learns are actually very sparse convolutions. So if you look at these probe voxels, which are learned automatically, they actually correspond to convolutions which are fairly lightweight. And this is key because this is what we managed to do is to come up with a learning scheme where the number of parameters is hundreds of thousands as opposed to millions or perhaps even billions, which allows us to learn from a small number of images, and also allows us to learn from a small number of examples, thereby avoiding the usual overfitting issues that one finds when there's not enough data. Yeah, so this is our way of actually thinking about what these convolutions look like. And at inference or test time, this is what happens. It kind of mimics the training process. So here we have 4 CT images, pelvic of course, for 4 patients, and each of these are fed to the machine learning model. So after iteration 1, which is the output of each of these images for after they're passed through the first layer of the forest, and what that means is that for every image, we evaluate the result of the forest on each voxel in the image, and these are the probabilities that you find. And these probabilities together with together with the original CT image results in another prediction of the next level of probabilities, and so on and so forth. And finally, the last layer produces the segmentation. So in practice, these, at least for this prostate model, the decision forests are very deep. So sometimes, for example, this model, which we have built for the prostate, is of depth 72. Right? So they're very deep and very compute intensive as well. We've also performed a fairly comprehensive evaluation of our method, where we've done interobservable variability studies, and what we find is that there is no significant statistical difference between the machine learning produced segmentation, which are the bars to the right, and expert observers, which is quite promising. Here's another application that we're looking at, and this is in radiology. So here's an example of a patient suffering from glioblastoma, and here's a temporal analysis using MRT1 with contrast. The patient here is being treated with chemotherapy and radiotherapy. So the clinician will look at these images, and the top row you will find that the tumor is responding to treatment, and it looks like it is shrinking. And in the bottom row, we find that the tumor recurs and grows quickly again. So with machine learning produced segmentation, which as you saw can be done pretty quickly, we can overlay the segmentation with these images to see that we can assess the progression via the volume of the enhancing tumor. Oops. And this is easy to do for other sequences as well, and here we've done it for edema using MR flare. And when we start plotting this on the graph, we can start looking at very different patterns. So we can see that at time point 9, the enhancing tumor, which is the lower graph, seems to be stable, but the edema has started to increase, and this could be a signal that the disease is progressing, for example. And in this case, this is what is happening, and the tumor reoccurs and this is a bad outcome for the patient. Another application that we've been looking at for segmentation is robotic surgery. So we've been working with folks who deal with the Da Vinci robot, and this is by Intuitive Surgical. And the question here is, how can we use segmentation in this case to help with 3D navigation during a surgery and also with surgery planning. So this is for the case of partial nephrectomies where the surgeon removes the tumor and saves the kidney. So to the left you see the segmentation produced by our algorithms, and this is useful for two purposes. We find one is it's useful for consultation where the clinician can explain to the patient with respect to why they need the surgery, and the second is that it's also useful for the surgeon. So because they're removing the tumor from the kidney, what the surgeon also needs to identify in the course of actually doing the operation is to figure out which artery feeds into the tumor, so that using the robot they can clamp the artery to restrict blood flow, and this gives them 20 minutes to actually remove the tumor. So we worked with Intuitive Surgical to figure out how our algorithms can actually be integrated into their surgery pipeline. So in terms of segmentation models, this is what we've been working on. We have models for 3 different applications, as I've mentioned in the past few slides. The first one is quantitative radiology, where we've been looking at multiple modalities of MR for brain tumors. The second one is radiation oncology, where we've been working on head and neck cancer, prostate cancer, and liver cancer. And the third one is surgery, where we've been building models for lung and kidney surgery, where the application, as you saw earlier, was planning. So as I mentioned, when we started the InnerEye project, our first model was trained over 50 images, and which is why the research was driven by how does one do effective learning from a very small number of images, which also led to the research on decision forests. Today we have ingested more than 50K images from a variety of partners, and we are training models with almost 1,000 images. And so needless to say, we are developing robust deep learning technology for medical image segmentation and beyond. So here are some salient features of the model. So we use convolutional neural networks, which have been trained on thousands of 3D training volumes. These are state-of-the-art models, which have over 32 million trainable parameters. The inference is done on full 3D volumes as opposed to patches, and can be performed in less than 22 seconds for the prostate cancer case. And again, we find that the accuracy is on par with clinical experts. So here is the prostate radiotherapy planning model, and this has been done in collaboration with our colleagues in Addenbrooke's. And again, we've done an inter-observer variability study, and the bars in blue are the results of machine learning, and the other bars are for the human observers. So this model in particular was trained on 400 images, and we tested it on 62 images. And as you can see, all scores are above 85% dice, which is pretty nice and comparable to humans. Yeah. We've also been exploring applications beyond cancer treatment and segmentation. So here's an example of one such application. So wet AMD, or age-related macular degeneration, is a disease that affects almost 20 million people worldwide and is the leading cause of irreversible vision loss. So here's an OCT, or an optical coherence tomography scan, and as you can see in the image, and this is an eye scan, and what this image is trying to say is that there's been a lot of leakage from the blood vessels, which blocks the vision for the patient. And in this particular case, we're using deep learning for developing personalized therapies for wet AMD. So this project forms a key part of Microsoft's collaboration with Novartis, and this was recently announced a few weeks ago, in fact. So what makes all these applications possible is the medical imaging workflow that we have developed over the past few years. This helps us build systems in a reliable and scalable manner. This is super important for a safety critical domain such as healthcare. And there are two key parts to the workflow. One is the training pipeline, and the other one is the evaluation pipeline. So all the stuff to the right happens in Microsoft or in the cloud, and the stuff to the left happens in the hospital. And this is how we collaborate with clinical partners as well. For instance, hospitals. It always starts by installing what we call an InnerEye gateway. And this gateway allows the hospital, well, this gateway connects the hospital to our platform. It also allows the hospital to upload images based on patient consent. The gateway also allows the hospital to evaluate the quality of the models. So when a new image is acquired and stored in the PACS, that is also sent over to our gateway, and the gateway basically anonymizes and compresses the image, as you saw in the demo earlier, and sends the image to the cloud. After that, we fetch the result and put it back into the hospital database, and this creates a seamless workflow where clinicians have the results available to them when they open the image. The second part to the right is training new machine learning models. And as you can imagine, in addition to the machine learning or the deep learning, there's a lot of tooling that's required to actually build these models in a principled, repeatable, and robust manner. So to do that, we have tools to filter data, tag images, correct ad segmentations, as you saw with the radiomics tools. We've also built visualization and debugging tools to help with inspecting the results, understanding that results are produced for the right reasons, and so on and so forth. And then furthermore, we also have training infrastructure in place on Azure, which allows us to scale out over hundreds, thousands, and even more images. And finally, we have infrastructure in place which allows us to deploy models for research purposes at a number of centers. So I want to add that all this work has been done in very close collaboration with clinical partners across the globe. This also includes our deep collaboration with Addenbrooke's Hospital next door. And the reason we want to do this is to make sure that our work is grounded in clinical reality. The next slide captures the essence of our work. It's a video from our research partner, the General University Hospital in Prague, and it's in the Czech language. So I hope the audio works. But it's in Czech. So.
Se zapojili do výzkumného projektu společnosti Microsoft InnerEye.
InnerEye je vlastně výzkumný projekt, který má otestovat to, jak funguje umělá inteligence při konturování kritických struktur a cílových objemů v radiační onkologii.
Vyšetření na CT lokalizuje možné cíle pro ozáření a lékař musí zvlášť na každém snímku manuálně zakreslit přesné obrysy nádorů. To je časově velmi náročné. Cílem výzkumného projektu je pomocí umělé inteligence snížit čas, který specialisté stráví nad každým souborem snímků.
CT pánve má zhruba mezi 150 a 200 snímky, takže je to zhruba 200 snímků.
Manuálně trvá tento proces zkušenému specialistovi u rakoviny prostaty 30 až 45 minut. Ukazuje se, že s využitím výzkumných nástrojů projektu InnerEye by tato doba mohla být zkrácena na pouhé minuty, a to včetně odborné kontroly automaticky zakreslených obrysů.
Místo hodiny teď máme 5 minut, k tomu řekněme 5 až 7 minut na opravu těch kontur, pokud nám nějakým způsobem nesedí nebo pokud je chceme zpřesnit. Takže sami vidíte, že ta úspora je prostě zásadní, třeba 5násobná.
So this is the InnerEye team. More information on the project can be found on our website. With that, I'll stop. Thank you.
When you create the vector for input, there is no input about the intensity of the CD?
Oh, there is. So I kind of oversimplified that. Basically, the whole objective of the algorithm is twofold. One is to kind of correlate these intensities to the final result, but intermediately also figure out what these vectors should be. So it could be intensity, it could be intensity plus 4, it could be all kinds of combinations. Yeah.
And also, what was the statistical rationale behind reusing your random forest result? So what?
Yeah, that's a great question. So the point is that initially you have access to the whole CT image, and actually what's happening as you go deeper and deeper and deeper is that we're kind of refining the region of interest. So the smaller the region of interest, so for example, if someone was to say, here's where the prostate is, and then we applied the algorithm, then presumably the algorithm is doing well, it would have more confidence with respect to the classification task, as opposed to saying, here's the prostate, and here like 6 million voxels surrounding it. So what's happening in every layer is that we are actually amplifying the signal by restricting the area of interest. So it's like so the way to look upon each layer of the forest is that it's like a likelihood function that's converting a prior probability into a posterior probability.
Thank you for the talk. I have a question about the pipeline you have showed, starting with flight control and sending the results. What is the automated part, or which parts are right in the learning? For example, does the quality control also do deep learning here, or is it manually done?
No, a part of that pipeline is the deep learning part as well. So for example, we've developed algorithms, of course, to do the deep learning. So essentially, it's like an experimental platform. So for example, if someone who's like a data scientist wants to kind of apply their own, let's say, model specification to a new data set, then the pipeline basically allows you to do that in a very convenient manner, almost like PyTorch, TensorFlow, and so on, but with scale out and for medical imaging.
And what you have now is mainly segmentation, or you have also for the quality control or for post-processing?
Yeah, so we have it for whatever the underlying algorithm is for. So for classification, for segmentation, and diagnosis as well. Yeah.
And for the segmentation part, you showed that you use deep learning for 3D segmentation and achieve still R. Can you mention which model is this, and or which organ as well to achieve it?
So we have models, as I mentioned, for pelvic CT, head and neck, and
Like 3D unit or?
Yeah. So the applications are what I showed was for pelvic CT, head and neck, and brain, and the underlying model is a variation of 3D unit. And we've also built something known as autofocus networks, a combination of all of those. Yeah. Thanks.
Just one more quick one. It seems like the applications right now is for workflow-related applications. Is there any R towards using for clinical decisions?
Yeah, in fact, the collaboration with Novartis is for clinical decision making. Yeah.
Okay, I think we have to run a little bit later, and we also have to do
Yes, so the plan is Chris is a photographer, we all go outside. Where should we go exactly, Chris?
Just in front of this building over
Right.
here, but you need to stand on the tiers of the steps. Talking to you.
Yeah.
There is lunch afterwards.
Yeah. Thank you.
let's